Hi guys, today in this small video we are going to discuss about the properties of binary operations. So we have already defined binary operations in last class. So it is actually a function from S crosses to S. So an underlying set is important, and if the output element A star B is again in S, then we will say that that binary operation is well defined. Now, as we are moving to the properties of binary operation, the first property that we are going to dealing with is the commutative property of the binary operation. So, in a binary operation, we are taking an element from S crosses. So, that element is an ordered pair. So, naturally, we will think whether the order is that important or what. So, we are thinking of classifying the operations where the order is important and the order is not important. So if the order is not important, then such a binary operation is called commutative binary operation. So a binary operation star on a set S is commutative if and only if A star B is B star A for every element A comma B element of S. So if I am taking any two pair of elements, both the ordered pair AB and BA give the same output A star B or B star A the same output, then we say that that binary operation is commutative. So we will move on to some explicit examples for commutative binary operation. Consider the set n of natural numbers and the binary operation addition. It's very easy. So here we are taking two elements 2 and 5. So we are adding it. 2 plus 5 is 7. 5 plus 2 also is 7. So addition is commutative on set of all natural numbers. What about set of all integers? Whether addition is commutative? Yeah, if I am interchanging n with z, the set of all integers, I can take z includes negative integers also, so I can take 2 and minus 3. So 2 plus minus 3 is minus 1, right? 2 plus minus 3 is minus 1. Then minus 3 plus 2 is also minus 1. So the set of all integers is closed or commutative with the binary operation addition. Now we are going to have a counter example. We are taking the same set of integers z, but we are changing the operation. What about if I am taking the operation subtraction in the set of all integers? Is it commutative or not? We will check. So here we are taking two elements 2 and 3. So 2 minus 3 is minus 1, but 3 minus 2 is 1. So they are not equal. So subtraction is not commutative on the set of all integers. These are very simple things. Now we have some remark. We have already learned of making some composition tables. Here we will write the elements of the set in columns and make the table, composition table. So if a binary operation is commutative, then there will be symmetry with the diagonal from the left corner to the downwards, this diagonal. I have put a line on that diagonal, so that diagonal will act as a mirror and symmetry will be there on both sides of the diagonal. If it is commutative, so we can have this observation on the composition table of the binary operation along with the set. Now we will go to another important binary operation. So in the case of commutative property, we were considering two elements A and B. Here also the operation will be going on between two elements, but what if we are having three elements and we are having some operations, so repeated operations. So I can do repeated operations in different ways. So I have A star B star C, that is what I want to operate. So first I can find A star B, then with that result maybe it is some K or P, so it is let it be K, then K star C I can do, so I will get some P. If I am changing the order of the operation, what happens? So if I am changing the order of the operation, first I will do B star C, so I will get some S, then A star S, I will get some Q. So if that P and Q are same, then we will say that binary operation is associative. Okay, so if that P and Q are same, we will say that that binary operation is associative. Now we are ready to define an associative binary operation, that is definition 2.1.2, definition 2.12. A binary operation on a set S is associative if A star B star C equal to A star B star C for all A comma B comma C element of S. So it can be shown that if star is associative, then longer expressions such that expressions with 4 elements, everything we can arrange like that, they will not be ambiguous. Then parentheses may be inserted in any fashion for purposes of computation. The final results of 2 such operations will be the same. So if once the operation is associative, we can take parentheses as we like. Okay, so this associativity property is also a very important one. Now, as an example, we are going to look the associativity property of composition of functions. So here the operation is composition of functions. So let us be the set. I am taking the set of all functions mapping S to S. Maybe I am having 3 elements, f comma g comma h. They are all functions mapping from S into S. Now I am checking whether the operation composition of functions is associative or not. So f composite g composite h equal to f composite g composite h. That is what I have to prove. So I will start from the LHS and I will reach somewhere. Then I will stop and I will start from RHS and I will reach the same space. So that is the proof. So we are having we start from LHS, f composite g composite h of x, that is f of g composite h of x. Again, g composite h of x is g of h of x, that means f of g of h of x. Now we start from RHS, f composite g of h, f composite g composite h of x, that is f composite g of x, f composite g of h of x, that is f of g of h of x. So here this and this are same, so we will get what the composition of functions is an associative operation. Now we are having another important property of a binary operation, that is having a particular element in the set. When that element is operated with any other element, no particular change will happen to that element. So we can say that element as identity element. So if a binary operation star on a set S is said to have an identity element, if there exists an element, E element of S, such that A star E equal to E star A for all A element of S. The element E, if exists, is called identity element of the set S under the binary operation star. So if I am having a set and a binary operation, it is not a must that that set will have identity element. But if that set is having an identity element, then we can say that that binary operation in that set is having the property of having the identity. Now again we are saying identity of element is a good for nothing fellow, because when it is operated with any element, the output will be that same element. No change will be done for that element. So we know identity. Now we will just discuss examples of identity. We will take set of all natural numbers. Is there any identity in set of all natural numbers? No, because the 0 element is not there in the set of all natural numbers. So no identity. Now if I am taking integers and I am taking addition, the operation addition, then 0 is the identity, because a plus 0 is 0 plus a is a. So in integers with operation addition, 0 is the identity. What about the integers with non-zero integers, that is set star with the operation multiplication? So if I am multiplying any number with 1, I will get that number itself. So if I am taking set star, then the example of the identity in set star with the operation multiplication is 1. So set star along with dot have an identity 1, but set plus or set along with set star along with addition does not have an identity, because 0 is not there. What about the space of matrix spaces, the set of all m by n matrices? What will be the identity? Of course, it will be the 0 matrix, 0 m by n matrix. It will be the identity because we are adding the 0 matrix to any matrix, we will get that matrix itself. What about functions, set of all real valued continuous functions? That is then binary operation will be composition. What happens? Okay, 0 function will be the identity. So now we are moving on to another property, inverse of an element. So already we know what is an identity element. So here we are going to define inverse of an element. An element B element of S is said to be the inverse of an element A element of S if and only if A star B is equal to E and B star A is equal to E for all A comma B element of S. Here E is the identity. So what is inverse? In the word inverse comes from the Latin word inversus. That means turning upside down. So whatever I have, if I am taking 5, what will the inverse of 5? It will be minus 5. So if A is an element and if A is operating the binary operation with its inverse, the output will be the identity element. So turning upside down or making us into nothing. That is the role of the inverse. So consider the set of all integers with operation addition. Minus 2 is the inverse of 2. So just we have to check on operating with what element I will get the identity. That element is the inverse. Now I have posted assignment already. So thank you for watching.